Hello friends, I am Anurag and in this video I am going to give you an overview of my semester projects for signaling system. My semester project of signaling system was based on music signal analysis and music genre classification. Now, music signal analysis and genre classification is a base of music app based industries like Shazam and Bing. Now, what they do is they first analyze the signal through certain mathematical functions like FFT and FFT, QFT, MFCC, etc. And they get a series of coefficients C1 to C1 to Cn. Now n depends on my accuracy, like till what n, like if like the classifier that I have made has used n is equal to 13 for MFCC and n is equal to 20 for FFT. Like it just increases the accuracy of the classifier. Now what they do is they first calculate C1 to Cn for each and every song. Like if I have 10 power 5 music song, then I will calculate 10 power 5 for each 10 power 5 music files. I will calculate C1 to Cn, and then what I will do is like uh, they will by help of humans they'll create their data set. Like if there are 10 classes of song, like capital C1 to capital C2, what it will do is what the humans will do is they will classify each and every song in each of these category. Like first song will come in C1, second in C2, third in C10 maybe, and like 10 power 5 so on, and 10 power 5 again in C1. So now hence they created their data set. Like this data set is created, like my music file is labeled, my music file m1 is labeled against certain class. Now data set is meant by this is my data set for every music file. This is J. Okay, so now my data set has been created. Now I will pass this data set to my classifier to train a classifier. Like I am training my classifier to get my models, like my weight files, basically my weight file, to get my weight file. Now as soon as I get my weight file, now this is my weight file. This is basically my model which I trained for 10 power 5 music files. Now if now my model has been created, now what I will do is like I will test run it and I will check the accuracy. If there is certain mismatch or the accuracy is not up to the mark or benchmark, then I will again train my classifiers on new set of data, on a good and new set of data. Like okay, so now if my classifier has certain accuracy like 85% or so, what I will do is I will commission it into my app. Now what that app will do is like if a new music file, suppose 10 power 5 plus 1. Now if this music file is passed through this classifier, what this classifier will do is it will label it. It will tag or it will label the new file in this in one of the classes of C1 to C10. Okay, so now my new music files are getting automatically tagged. So okay, so now so one of the main function of my classifier is to tag music files, tag new music files. Now what is the application of this? The application of this is that if I am a consumer of that music app and I am listening to a particular kind of music, like if I am listening to jazz kind of music, now what this app will do is the app will go through my history check my records, like what kind of music I am listening to time. Like, and if the app checks my history in 15 days, and the app checks that I am listening to I'm listening more jazz music. So what this app will do is it will suggest me more jazz music. Like, it will go through its directory, and all the jazz music will be suggested to me, like all like it has 10 power 20 music files in its data, like, and 10 power 10 has been jazz. So all this 10 power 10 will be not at the same time, but at different instance of time. The app will suggest me this particular jazz music. So basically it's providing me a more number of choices with the same kind of music I like to listen. So it's making the consumer life easier. Second thing, it is tagging music files on its own. Third, it's creating database for consumer also, like how many consumers like jazz music, how many consumers like hip hop music and all. So uh, so this kind of application, this kind of classifiers are important in music and signal analysis based industries, and there is a proper committee which is working on it. Okay, so now without wasting our further time, let's get back to the mathematical details that we will need to go through it. So our first basically we will analyze this signal, like by running. Wait, now first we have to run through my code. Like, first we have to convert our audio files into wave file. Now this is just a format of files, like, and this can be done by running through mp3 to wave file. Like, I have given a code in my github link also. Like, we have to convert using using librosa module, or using scipy module or pydub module. We can convert a audio file to wave file. Like, audio file is an mp3 file, and a wave file is a chunk. Will give me wave file give me the audio file in numpy arrays. So basically I am converting my this thing into certain number, because I can only manipulate numbers in Python code. So it will give me a wave file. Now second thing is, like, now I will plot this wave and see whether how two classes of music are changing. So let's run one of the codes. Where is it? Yeah, waveform code. Like, first I have taken a hip hop file, and second a classical file, and I am running this. So I'll get it's taking certain time. Okay. It's taking some time. PC is slow. Anyways, now it will appear. So second thing, let's get back into the formal mathematical background of signals and analysis. Like, how we will analyze music signal, or any kind of signal. So the first thing that comes to our mind is FFT, that is fast Fourier transform. Basically it's a Fourier transform, and the F is added because the algorithm that is used to compute Fourier transform in by a computer or in a coding language is computationally faster than normal Fourier transform algorithm used in computing Fourier transforms. So the mathematical definition of this is, like, we will map xk to certain yk. Like, basically we are converting our time domain music system to frequency domain. So which will be get now what it does is fast Fourier transform samples time signals over a period of time and divide it into its frequency components. Like, if my signal is made of this frequency, this frequency, and this frequency, and I have overall signal as this is this. Now if I pass through fast Fourier transform, Okay, the graph is open, so you can see that my hip hop file is more ups and downs, like it in a short number of time, like you can see it's rising up and then coming down. The amplitudes are going up and down very frequently, and for a classical music it's more or less it's more smoother than the hip hop. So we can see there is a difference between hip hop music and classical music in normal waveform itself. Now let's get back to the fast Fourier transform. So when I'll pass my original signal from a fast Fourier transform algorithm, it will give me this. It will divide it into its frequency components, like this frequency component, this frequency component, and this frequency components. Now, what is the definition of fast Fourier transform? Now, like it's xk equals to sigma I if I okay, it is subscript of n by n, where n this is n, like if this is my frequency thing and this is my time domain thing, so this will change according to this. This is the definition of Fourier transform, which is basically it's discrete Fourier transform. That's why it has sigma. Since computer cannot calculate a continuous waveform, like computer we have converted our uh, audio signal into wave file, which is a discrete set of points. Now each and every discrete set of point will be passed through this, so we will get a frequency function of our wave. Now second is spectrogram. Yeah, we have now if I pass through, now this is the frequency transform of my both signals. Like you can see, if I pass both wave files through a FFT algorithm, this will be the output. Like you can see here and here, like there is more. The classical music is in the region of 10 power 5 hertz and more, or in the less than 2 into 10 power 4 hertz and below, and that's all. And in the next thing is our spectrogram. Like what a spectrogram does is, spectrogram basically is a visual representation of frequency with time. Like in the wave file we see that the amplitude changes with how amplitude changes with time, but in spectrogram we will see that how frequency changes with time, and we also have a graph of that. Now this is the graph of spectrogram. all the co- all the codes has been provided in my GitHub link, so you can go through that, and the spectrogram also. And this is the file of spectrogram. Like you can see how hip hop music files spectrogram looks like, and how classical music file spectrogram looks like. Hip hop file is basically more lines, more fringes in it, and spectrogram is more basically is getting faded when it moves to upper side, and has more smoother part in the lower side. Now the next thing is Qtransform. There is one more thing before Qtransform, and that is STFT, like short time Fourier transform. Now one of the reasons of using STFT is that in fast Fourier transform we use full wave file. Like in FFT, if I have a 2 minute of audio clip, like if I have 2 minutes of audio clip, I will use whole 2 minutes of audio clip to pass through it, and it will give me uh, its own, like it will give me this kind of plot and this kind of plot. Now other efficient way to do is, like if this is 2 minutes of audio clip, what if I divide or fragment it into 30 seconds of audio clips of 4. Like first I will pass this from a Fourier transform, then I will pass this from a Fourier transform, I will pass this from, then I will pass this, and then I will pass this. Like I am doing four time four I am doing the Fourier transform four times on same file but on different segments, so it will give me a better results than normal Fourier transform applying on 2-minute file. So that's what STFT is. STFT is basically Fourier transform. Basically STFT is a Fourier transform but on a shorter period of file. Like basically it's a Fourier transform but on a shorter period. Like first it will that depends on how I choose a window. Like if I have chosen a window of 30 seconds, then every then for then the fast food transform will happen at 30 seconds of the interval. Like I have given example in the previous Pygame window. Okay, now this next thing is Qtransform. Now Qtransform is related to Fourier transform. It's a series of logarithmic it is a series of logarithmic place filters FR with kth filter has been having spectral width of delta fk. Like delta fk is basically given by this definition, 2 power 1 by n into delta fk minus 1. Now this is a recursive formula, and this can be written as 2 power 1 by n delta f minimum. Now delta f minimum is nothing but central frequency of lowest filter. Now and the definition of Q transform is given by k1 is equal to sigma w n minus m x power n x the n into e power minus j 2 pi, sorry for bad handwriting, 2 pi k subscript n divided by n, where this n minus m is my Hamming window. So and n of k is my window length, and n of k is my window length, like for how many windows I am doing. Okay, so the next thing, so my next thing is MFCC, which is advanced, more or less advanced features than FFT or Qtransform. What is this? It's the short-term power spectrum of the series. Like it will basically give me power spectrum of my series. Power spectrum is nothing but it's given by mod of inverse of Fourier transform of log of Fourier transform of f of t. This is my MFT coefficients will give me, and it is much more efficient than Fourier transform, as we will see in the given classifier. Now let's see the graphs. This is of a Qtransform graph, of hip hop and classical. This that was a chromogram. Okay, I will tell you what a chromogram is. Now chromogram is basically when we add a chromogram in a Qtransform, it will give me a pitch class, like how my pitch is varying. It's one extra information that is given by Qtransform, and that's why we can see the difference between the graph. Like here the pitch is varying more in hip hop and the pitch is varying less in classical. Like pitch is very smooth in classical, more or less smooth in classical than hip hop, as we can see how the pitch value is changing. And this is the Qtransform, like power graph of hip hop and classical. It as we can see that there is more power in hip hop music and less in classical music. Less basically classical music is smoother than hip hop music. Sorry. Now, do we have any other? This is a power spectrogram, as we talked about. Like it's a log of power spectrogram. So we can say, like as we have seen in Qtransform, the graph is more smoother in the classical side than in the hip hop side. So basically, based on this, we can say that if based on this, we can say that we can easily classify certain songs into certain classes, like hip hop songs can and classical song can be classified. If I give a file, if I give a music file to my classifier, it will successfully classify that file into certain genre. Like if it is hip hop, it will classify it into hip hop. But I have given a music analysis for only binary class, like if it's 0 and if it's 1, then I have taken only two classes for music analysis, but same thing can be applied to other n number of classes if there are any. There are n number of classes for classification. Now let's move on to our classifier part. Now in this classifier, I have used an SVM based classifier, that is support vector machine classifier. And now what it does is, what SVM does is, if I have a graph and these are my data points and these are certain data points, other data points, sorry, these are my graph, these are my 3 data points. Like if I have overall of 6 or 7 data points, and these are my data points. Okay, now what it does is, this SVM is a supervised learning. So what it will do is, it will first see all these data points and it will try to find a hyperplane to differentiate between the two classes. Like if I train my classifier on this data point, the SVM will try to find this hyperplane, which will give me the best possible value of certain equation, like ax plus by, which will successfully classify new data points. Like if I passed x4 data and it lies in this, so it will this hyperplane will classify this data point in the x class and not the 1 class. So basically SVM does is, SVM gives the equation of hyperplane. Basically it's the boundary between the classes. So let's see what we have to do basically to run the classifier. So basically first we have to convert all the data points, like like basically the data was in the form of audio, as you can see, like this is the audio file, which is a VLC file, and now we have to convert it into wave file. Like this was my wave file. You can see in the disk icon, like this is my wave files. This is my wave files. This. So which we converted using the music to MP3 to wave conversion program. Like this, MP3 to wave. Wait a sec, yeah. This by using this function we converted our files to wave file. Now if we have to extract the features using FFT, like if we are using FFT features, so we have to first find the coefficient of FFT. Like if my wave1 file has C1 to C20 coefficients for FFT, like this is the feature vector of my wave1 file. So first I have to extract that. Now how will I extract that? extract that, like by using this code. Like you have to first we have to create the FFT features. Like we have a SciPy module in Python that will, what that will do is that will extract the FFT features from fast Fourier transform, and that's been n is equal to 1000. So 1000 coefficients of fast Fourier transform will be extract, first 1000 coefficients of the fast Fourier transform will be extracted as FFT features, and then it will be write into a new file, that is my this file. Like if I have passed sorry if I have passed blues of blues 1, then this file will be generated for basic. This is nothing but this is a FFT feature file, which is first 1000 coefficient of Fourier transform. And sorry it is, yeah, FFT file. Now by running this program, I have already run this program in my PC, so that's why I have all the FFT features file. Now by running this code, we will get a FFT features file, and that feature file will be fed to my FFT classifier. Now this FFT classifier, see, as you can see, if main. Now this FFT classifier will be trained on that data. Like we have extrained first, no, sorry, if like I have given 100 songs, then first I will divide that 100 songs into my two data sets. Like first will be test data and the other will be train data, and that will be converted. Like the test size is 0.3, so 0.7 of the overall data is my train data. I will train on 0.7 into total number of files, and I will test the errors based on 0.3 test files, 0.3 into overall number of test files. So using scikit-learn, I have trained the classifier, and I have used SVM classifier, and I am not running it again and again because I have already saved the model, so it's no use of running. So basically I got this as my confusion matrix. Now what is the confusion matrix? Let's see. Now this is a confusion matrix. If my predicted class, this is side is, sorry, y-axis is my predicted class and z-axis is my true class. If my predicted class and z class match, then it will be darker, like hip hop. If now FFT based classifier are so bad classifier. Like we can classify based on FFT based, but as we can see, FFT based classifiers are not up to the mark. So if a classifier is up to the mark, then the confusion matrix diagonal should be dark than other matrix diagonals. Then other elements, like in this blue, no one can identify what blue song is. In this classical, it's been classified as disco or blues, and in this no, and in the hip hop is classified as hip hop. So basically my classifier is only classifying hip hop as hip hop, and other are not getting classified within a certain limit. So I have to move on to the next classifier. Like what will be my next classifier? My next classifier will be MFCC based classifier, that is Mel frequency based classifier. Now Mel frequency based classifier uses power spectrums as its feature vector. Power spectrums, what power spectrum? Like log of P. Like this will be the feature, this will extract the feature for the music file. Now how will do this? Where it is, yeah. So steps is basically, this will extract the feature. Like first the same procedure we will, but in this case I'll be using librosa to extract the MFCC features. So in this case this create steps will create my MFCC coefficients, and then write steps will create a file of MFCC coefficients, and then this will be fed to my steps classifier, which is nothing but, again, the all procedures are same, like confusion matrix, data set, confusion matrix, train and data set, test. Now I have changed the test size and then the code. Like here we are using SVC classifier, same as before, and then when I will run this code, my confusion matrix will look like this. As you can see, it is more concise, it is more better than the FFT based classifier. As you can see, my all songs like metal is getting rated as metal, classical is getting rated as classical, hip hop is getting rated as hip hop, blues is getting rated as hip blues, and this all. So MFCC based classifiers are better than FFT based classifier, as we can see, because it is more advanced feature than FFT. Basically we are using log, so error is getting reduced. Now two more, there are other now, yeah, as you can see, as we have seen the, yeah, now here, in the end I want to conclude that, as we can see, there is still more progress in classifier, there is still more progress going on in classifier for signals, because the diagonals are dark but not rest of the elements other than diagonals are white, or like in a dim shade. So there is a little chance, there is a probability that my metal can be classified as hip hop, my hip hop can be classified as reggae, my pop can be classified as hip hop. So there is little probability that my songs can be classified in other classes also. So basically what my future goal is to yeah, like this auditory filter bank temporal envelope features which outperform MFCC in certain situations. So basically there are more features which can outperform MFCC also. MFCC is a good classifier, like it gave me it gave me the accuracy of 85%, I guess 85 or 87% accuracy. So basically it's a pretty good classifier, but we had if we had to reach to 95% accuracy, we have to use other features also, or a mixture of features like FFT, MFCC, auditory classifier, etc. And thanks to ISMIR paper, like basically ISMIR is a music community that works on this classification thing. So thanks to ISMIR paper and their blogs which helped me to complete this project. Okay, so yeah, and I have used following tools, and the dataset that was used was GS10 dataset. It is a basically benchmark dataset for audio file classification, and I have overall size of the dataset was 1.2 GB, but I have reduced the file size, like I have used less than 1 by 4th of the dataset because of the PC constraint. Okay, so thank you, I guess. And report and codes are attached in the reference of the video. Thank you.